Welcome, ladies and gentlemen, to the free response question review. In today's episode, we will be discussing the 2012 Calculus BC exam, question number 1 from the graphing calculator portion. This problem also made a guest appearance on the Calculus AB test that year as well. And it's a standard table problem with some Riemann sums, some derivatives at a point, and some integrated one math. So let's go ahead and get ready to get started. We have a table here with some values. The temperature of water in a tub at time t is modeled by a strictly increasing. That sounds pretty important. I'm going to go ahead and underline that. Strictly increasing. Twice differentiable. That sounds kind of important also. Function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes at time equals 0. The temperature of the water is 55 degrees. The water is heated for 30 minutes beginning at time equals 0, and values of w of t at selected times for t for the first 20 minutes are given in the table above. So this table here is a representation of the temperature of the water at that moment in time. So this table is not representing a rate. So what we see is what we actually get. So with that in mind, let's go ahead and take care of this problem. It says, use the data in the table to estimate w prime of 12. Show the computations that lead to the answer, and using correct units, interpret the meaning of the answer in the context of the problem. So if we're going to figure out w prime of 12, I'm going to want to squeeze that 12 in between two times that I am aware of. And those times are going to be most accurately represented by 15 and 9. Right? Most people will ask, well, why can't I just use 20 and 4? Well, you can. It's just not going to be as good of an estimation. You want to squeeze your number in between the two closest things to it. So from here, w prime of 12 will approximately be w of 15 minus w of 9 over 15 minus 9. So what is that really? Well, that's 67.9 minus 61.8 over 15 minus 9. Now at this point, I would probably recommend you just stop solving it from here and just not simplify, because this will give you the first part of the answer. Now from here, because I'm going to actually interpret this, I'll go ahead and just let you guys know it's 1.017. And again, this is a calculator problem, so it's really not that hard to figure out after punching a couple of buttons in. So what does this mean exactly? Well, from here, this is going to be in degrees Fahrenheit per minute. And since we have to actually interpret that in the context of the problem, what we're going to say is the temperature of the water changed by 1.017 degrees Fahrenheit per minute at t equals 12 minutes. So again, we used the correct units, we used the correct interpretation, so I think that would be good enough to satisfy part A. Let's go and move on to part B. It says, use the data in the table to evaluate the integral, the definite integral from 0 to 20 of w prime of t dt. So w prime of t dt. Okay, so we're going to evaluate this now. So using the first fundamental theorem, that would get me w of 20 minus w of 0. And what is w of 20 minus w of 0? Well, w of 20 is 71, and w of 0 is 55, and we're subtracting. That gets us 16 degrees. Now, if we're going to use correct units, and if we're going to interpret the meaning of this in the context of the problem, well, if we integrate the rate at which the temperature is changing on an interval, we are calculating the total change of the water's temperature. So that's what we would say. We would say the water's temperature changed by a total of 16 degrees Fahrenheit on the interval 0 to 20 minutes. So again, when we integrate a rate on a definite interval, we're getting the total change in what we were evaluating. So hopefully that makes a little bit of sense. Now we got to move on to part C. Part C is asking us the average temperature of the water in the tub is modeled by 1 over 20 integral from 0 to 20 W of T dt. And so we're going to use a left Riemann sum with 4 subintervals to find out or approximate how much this is, and then we'll figure out if it's an underestimate or an overestimate. Okay, so we can do this. I'll go ahead and draw the graph. I like to graph my Riemann sums. It is entirely up to you. I'll go ahead and switch colors here. So at 0, I'm at 55. I'm going to go and put that a little bit lower because I know this is a strictly increasing function. That's 0. At 4, I'm going to be at 57.1. At 9, I'm going to be at 61.8. At 15, I'll be at 67.9. And at 20, I will be at 71.0. Now I'm using a left-handed sum, so I'm going to go ahead and just draw my left-handed rectangles down here. Left-handed rectangle here, and left-handed rectangle here. And then what I'm going to do is I'm going to go in on the side here, on the side write down the integral with my average value on the outside. Now again, in Calc AB, I don't believe this is going to be an issue coming up this year because average value has been taken off the AP exam, but BC, you definitely want to be ready for this one. Average value is probably going to show up. So that's going to be my left-handed sum. My first base is going to be 4 with a height of 55 at that moment in time. My next base is 5 with a height of 57.1 at that moment in time. And then plus a next height of 6 with a height of 61.8 at that moment in time. And then my last will be 4 with a height of 67.9. And all of that will get divided. I'm going to move over a little bit more. All of that will get divided by 20 or multiplied by 1 over 20 for average value. And again, since it's a calculator problem, you just input all that stuff into the calculator. You'll end up getting 60.79 with no third decimal. So I know the AP exam wants to go to 3 decimals. This time there was only 2. Now in this case, they want to know if the estimation is an overestimate or an underestimate based on what we're seeing. Now the reason why I underlined certain parts of this problem here, the strictly increasing was a dead ringer for part C. So if we look at this function as strictly increasing, and I'm going to say regardless of concavity. Regardless of concavity, if I'm concave up, it looks like my rectangles were underneath, even though I'm increasing. If I'm concave down, my rectangles are still underneath. If I'm concave up, we're still underneath. So either way, the rectangles are underneath, making this an underestimation. And the reason why will be because of our left-handed rule. So let's go and write this down. W of t is a strictly increasing function on 0 to 20. Move that down. And therefore a left-hand rule will be an underestimation. And we had just enough space for that, so I think we lucked out on that one. Excellent. Okay, let's go and move on to part D. I'm going to go and clear off the board a little bit. If you need to, go and pause and make sure you have all this stuff written down. Let's go and clear you off here. And then it says, for part D, it says between times 20 and 25, the function W that models the water temperature has a first derivative given by this thing. And based on the model, what is the temperature of the water at time equals 25? Okay. Well, from here, part D. What I'm going to do is I'm going to go back to something we've done before. If I'm going to find out the temperature of the water at time 25, well, I better have an anchor on this thing. This is going to require the first fundamental theorem of calculus again. I'm going to start at 20, and then I'm going to go to 25, and I'm going to integrate W prime of t dt. And that's going to get me W of 25 minus W of 20. Now I know W of 20. W of 20 is 71. So that means that W of 25, when I get it by itself, is going to be 71.0 plus the integral from 20 to 25 of w prime of t dt. And when I add those things together, I should end up with my final answer. So let me show you what this looks like in the calculator, because there might be some Calc AB students who are watching this. I've got my function in here. This is the function given to us in part D. So I graphed it. Whoops. I'm going to graph it, which is going to end up becoming right here. Cool. So let's go ahead and just figure this thing out. So I'm going to go and integrate from 20 to 25 of f1 of x dx. I'm going to hit enter, and then from here I'm going to add 71.0 to it to get this number, 73.043, and I punch that in, 73.043, and I believe that is the final answer. And with that, I believe that will wrap it up for this question. As always, please leave comments or questions in the comments section, and we will clarify those as soon as we can. I will see you in the next episode.